It's laser time in Dave's garage, and today I'll show you how to make it. Hey, I'm Dave. Welcome to my shop. This weekend, my mom sent me an ad for a cool Giga on Facebook that looked kind of like what you just saw, and I scoffed that I could write that on a Monday morning. She pretty much called me on that, so I very much had to go ahead and do it. Now granted, I use the NightDriver software package to do the heavy lifting, and today I'm going to show you exactly how to build this effect on the cheap and easy. I'll take you through all the steps from connecting your very first LED on through everything you need to know to pair NightDriver with individually addressable LED strips in order to build some truly fun and compelling projects. Best of all, it's all completely free and open source. It's easy to get started, and from there you can modify, customize, and create new effects to your heart's content. To briefly summarize the technology, an individually addressable LED strip gives you complete control over the color and brightness of each LED on the strip. Unlike a conventional strip where all the LEDs must be set to the same color and brightness, each one on an individually addressable strip can be controlled independently, giving you the ability to create some very powerful effects. So from here on forward, when I talk about LEDs or LED strips in this video, I'm speaking specifically about the individually addressable style, and you can find links to any parts I use in the video description. As a few quick examples, here's my patio umbrella with the strips running NightDriver on all 8 of the spokes. It runs any effect you can think of, from flames to dancing lights to solid ambient colors. Now in a similar vein, we find the atomic fire lamp, which is a simple LED lamp that I grabbed off Amazon. It features 4 spokes where I replaced the factory white LED strips with individually addressable strips and then added NightDriver to control them. And here's my desktop PC fans running NightDriver. The code also supports strips arranged in circles, so you can animate the LEDs radially or in any direction. Best of all, by the end of this episode, you should be able to build any of these projects just by changing a single line in the NightDriver configuration without writing any new code. If the chip module that you wind up using to drive the LEDs features a microphone, NightDriver also supports sound processing, so you can make your effects sound reactive. Here's an example of LED strips arranged into a simple matrix to form a music spectrum analyzer. It also features several interesting sound reactive effects that track the music. The sound processing features beat detection, so you can have elements of your effect trigger on every beat of the music, making it the ultimate light organ. We're going to use it to launch a laser shot on every strong beat or loud sound that we hear. Let's take a look at the parts we're going to use today. The first thing we need, of course, is an individually addressable strip. What you're looking for is something compatible with the WS2812B standard and running at 5 volts, ideally. And again, I've put Amazon links for everything that I'm using here in the video description so you can find them easily. I've selected this strip from BTF Lighting, and they've earned my loyalty over the years by making a reliable product at a good price. They even offered to sponsor this episode, but I said, nah, to keep things independent. But I'm still happy to recommend them. The next thing we need, and in fact, other than a few connectors, the only other thing we require is an ESP32 chip module to control the LEDs. Now, the difference between a bare ESP32 chip and what's known as a module is that the module has a power supply, serial port, an LCD display, a battery, accelerometer, microphone, and various other peripherals all built in. They're cheap and easy to find on Amazon, and as little as $3 if you really want to hunt around on AliExpress and wait on the international shipping. For this project, I'm going to use a module known as the M56C+. The ESP32 inside has a dual-core CPU, Wi-Fi, Bluetooth, and it runs at a fairly fast 240 MHz, so it's not your grandpa's Arduino. This module also includes a number of extra features like a microphone, a color LCD display, infrared remote control transmitter, a 6-position accelerometer, and so on. But since we need the microphone on our project, it's a good choice. It comes in at around $35, but I think it's worth it given all the extra features, particularly if you're just getting started. You'll use it over and over as you learn new things. Let's have a look at how the module communicates with the strip. It's going to prepare and send a square wave signal that contains little batches of 3 bytes each. Those packets contain the color data encoded in 24-bit RGB, one for each LED. In between frames, there'll be a gap of at least 6 milliseconds, and that signals the start of a new frame. Now, there's no configuration or setup to be made between the chip and the module. The chip just sends as many packets as you wish, and if you have more color values than you have LEDs, they simply spill off the end harmlessly. And if you have too few, your colors won't reach the end of the strip, and that's it. Now, fortunately, we don't need to know anything about this, as the software side is all handled by NightDriver, and the hardware we need is self-contained in the module. You'll simply install the code on the module and then connect it to the strip, and then the magic happens. But before any real magic can happen, though, we need to set up our hardware. The good news is that there's only 3 wires: power, ground, and a signal. That's all we need. To get started, the first thing we need to do is supply power to the strip. The M5 module itself can be powered off USB or with a USB-C adapter, and we'll use a small power brick to run the strip. Now in theory, you could supply the whole thing off the USB power, but once you get past about a dozen or so LEDs, you're asking for more power than the port can normally supply, so it's just good practice to power the strip independently. To do that, I'm going to connect a female barrel jack adapter to the red and white lines of the strip, which are power and ground respectively. Then I can simply plug the strip into a power brick of matching voltage. Nothing will happen yet when we apply power because without any data, the LEDs all default to the off state. Now, strips normally come in 3 primary flavors: 5 volt, 12 volts, or 24 volts. It doesn't matter which one you have as long as your power brick outputs the correct matching voltage and that the ground, but not the power, is shared between the module and the strip. And so let's connect the module. There are 2 ways that you can connect the M5 module to the strip. Either way, you'll need a connector. The simplest way I figure is to grab what's commonly known as a Grove port connector, which has 4 wires coming out. It supplies a connection for the ground signal, the power signal, which we'll ignore, and 2 signal lines, of which we need only 1. And so the port has 4 pins, of which we're going to connect only 2. You'll leave the module's red power wire and the second data wire unconnected, as they're not needed for this project and can cause problems if you do connect them. At the other end, the M5 module also has a standard female header connector that exposes 8 of the chip's lines, including ground, power out, power in, battery, and then 3 signal lines. If you prefer, you could just use an 8-pin header and connect the ground and the line labeled as G26. If you do go this way, you'll need to change a single line in the configuration to change the output pin, and I'll show you that when we get to the code. The final connection is from the module to the strip. The power lead from the strip is not connected to the module, so leave both red wires unconnected. This is especially important if your strip voltage is anything other than 5 volts that the module is expecting. Regardless, the ground must be shared between the strip and the module, as the signal line requires a ground reference that both can see. We then connect that one signal line, which is green in most cases, and we're done on the hardware side. With the hardware all set up, what we need to do next is to load the NightDriver software. Now this is simple, but it requires a couple of prerequisite tools. First, you'll need to install Git if you don't already have it. I've put a link to that in the video description. Once Git is installed, you execute a single command line to copy down the code. That will copy all of the code into a new subfolder called NightDriver strip. Next, we need PlatformIO, which is going to be our build IDE, and it will compile and upload the code to the module for us. Now, there are plenty of videos on how to install PlatformIO, including one I made a year or so ago, and links are again in the video description. It's an extension to Visual Studio Code, so start by installing VS Code and then adding the PlatformIO extension, and you're ready to go. There are only 2 lines that we need to worry about in this entire project, and that's the default environment, which tells it which of the many NightDriver strip configurations to use and which serial port to upload on. If you're using the M5, you can simply make sure the default environment line is set to laserline as shown here. Finally, we need to tell PlatformIO which serial port, the module is connected to. Plug it in and use Device Manager Windows or the Devices tab in PlatformIO to find the name of your port. If you only have a single port, you can actually leave this blank and PlatformIO should find it for you, but to be safe, find the section of the PlatformIO.ini file labeled as laserline and then change the upload port and the serial port to be whatever you discovered it to be, like COM3. With that, we're ready to build and upload the code to the module. To do so, we press F1 to bring up the command palette and then select PlatformIO Upload. It should chew away for a minute and then look for the module on the port and upload the code. If it fails, double check your serial port as the likely culprit. The code will always compile and work right out of the Git repo as is. With that, the code will run as soon as it uploads and reboots. Now if you're using the M5, you'll get a simple little screen on the LCD with some stats about the running project and it will be ready to generate your laser effects. I'm using 2 300 LED strips chained together to get some length for the demo, but it should work equally well with whatever length of strip you have. Let's have another look. Now remember, the chip itself won't make any sound. That sound you're hearing is just an effect I downloaded from the internet, and I'm playing it over the shop speakers from my PC. The board will react with any significant change in sound level, so you can clap your hands or say pew pew or whatever you like to trigger the LEDs. If it doesn't work, check that your strip has approximately the right voltage at its tail end in order to confirm that it's being powered properly. Verify that the data line is connected and that the ground is shared between the strip and the module. If you're using the Grove connector on the M5, the pins will match the default configuration. Everything should work right away. If you're using the header connector, it's a different output pin, so we need to change one more line in PlatformIO.ini. If that is the case, find the section called laser line where your serial config was also listed and change the line that reads LED pin 0 equals 26 to whatever GPIO you've connected the data line to. Then rebuild and re-upload the code and you should be ready to go. There are dozens of project configurations listed in the ini file, and while building for other modules is a topic for another day, you can build any of the projects that make reference to the M560 and they should work right out of the box. Writing your own effects from scratch is also beyond the scope of today's video, so make sure you subscribe to the channel if you want to see more projects in detail. For now, let's look at the only effect we'll be running, which is the laserline effect. This effect is defined down in include effects strip laserline.h. Our laserline effect simply derives from two base classes, beat effect base 2 and LED strip effect. The former provides the sound integration so that the microphone can actually hear things, and the later provides us with a canvas on which we can draw to our LEDs. The init function makes a record of the GFX pointer, which is the pointer we need to call functions like setPixel to actually do our drawing. It then calls the base class init function to do whatever basic setup the effects require, and that's all handled for you. We only need to provide two functions, draw, which does the obvious, and a function callback named handleBeat. This function is called by NightDriver whenever a beat occurs in the audio. Up in our constructor, we passed two values to the beat effect base 2 class. The threshold from 0 to 2 on how loud that beat must be, which we set to 1.5, and a minimum duration that has to occur between beats. To ensure we don't miss rapid-fire sound effects, I'm setting that to 0, meaning no delay needs to be found in between the shots as long as the volume exceeds that 1.5 threshold. When it does, you can see that we have a vector or array of shots. We create a new one and push it onto the array, and that's all we need to do in the handle audio case. Our draw call must first call process audio, as that's what does the fast Fourier transform that actually analyzes the incoming sound for you. Next, we fade the entire strip out by some amount. You can specify a value from 0 to 255, and the LEDs will be dimmed by that amount every frame. I found that a good value for this project is 200, and it gave a pleasing trail behind the shot. We then walk the array of shot objects and call each of their draw methods, which we'll look at in just a moment. Next, we call its update function, which will move the shot and return a value of false when the shot has gone off the end of the strip. When that happens, we erase the shot from the list. That way our array can hold any number of active shots, but they expire as soon as they hit the end of the strip and then clean themselves up automatically. This mysterious shot object is just a small class right above the effect itself, and it simply tracks the shot's position, speed, and color. It only has two methods, update and draw. The update function is responsible for moving the position of the shot. It receives a value indicating the fractional number of seconds that have elapsed since the last draw, and so the speed of the shot is the same regardless of the number of frames per second that are being rendered. As noted, if the shot reaches the end of the strip, the function returns false to advise the caller that it has gone off the end. Otherwise, it returns positive to indicate that it's still alive and active. The draw function simply walks the pixels beginning with the start position and finishing after the number of pixels corresponding to the shot's size have been drawn. We calculate the color of the shot using a CHSV class for hue, saturation, and vibrance, which allows us to specify a hue from 0 to 255 indicating the base color, and then we fully saturate it and show it at maximum intensity. And that's all it takes to render an effect via NightDriver. NightDriver also supports remote drawing complete with buffering to smooth out the Wi-Fi of any dropouts, so in theory, once you have it running, you can render and control everything you see directly from your desktop, but that's a more advanced topic. You can even render an effect using your GPU and then send it to the strip over Wi-Fi. For today, we've done everything without writing a single line of code, but the code's all on GitHub for the adventurous or those who want to contribute. Now, we're especially looking for somebody to contribute to the UI side of things using React. It's an interesting project in that everything runs out of the flash ROM on the chip itself, and the web server is hosted on the ESP32 chip as well via the built-in Wi-Fi. If you're a React expert, please stop on by the GitHub repo in the video description and lend a hand. If you have any interest in matters related to autism, Asperger's, or ASD, please check out my book on Amazon, Secrets of the Autistic Millionaire. It's got nothing to do with money and everything to do with living a successful life on the spectrum. It's everything I know now that I wish I'd known back then. Remember, I'm mostly in this for the subs and likes, so please be sure to leave me one of each before you go today. In the meantime and in between time, I hope to see you next time, right here in Dave's Garage.